So good morning, welcome back. Today we are going to discuss spin, or rather spinor fields on curved spaces, but also on curved space-times. And spin on curved spaces, curved space-times, is a topic that cannot be made precise without the full formalism of principal bundles, associated bundles, and so on. So this is another honest application of what we did. So that's 6.2 spinors or spinor fields on curved spaces and space-times. And in order to develop the definition of what a spinor field is, well, it will be a section of an appropriate bundle, and that appropriate bundle, that spin bundle, will be the associated bundle of some suitable principal bundle, okay, will be the spin frame bundle, that principal bundle. But in order to write down all of this, we need some preparation. And the first thing we need to look at is, is the spin group. So spin groups. What is a spin group? A spin group is a double cover. I'll explain that in a second in this context. That's a more general topological notion, but in this context of Lie groups, it's quite simple. Is a double cover of the special orthogonal group SON. So that would be the group of all the linear maps from Rn to Rn such that an inner product is kept constant. But because if we're just on a vector space Rn, we can always use Sylvester's theorem, and if it's a positive definite inner product, we could equally well take the standard inner product. So that is if Rx, Ry equals xy is kept constant, and this is the standard inner product on Rn. So xy is defined as the sum I equals 1 to n xi yi. Okay? So the spin group is a double cover of the special orthogonal group. What does that mean? That means we can construct a Lie group homomorphism from that spin group, and that spin group will be called spin of n. Okay, that is its official name, spin n. And we can construct a Lie group homomorphism. So, of course, in the context of Lie groups, the twiddle doesn't mean linear. There is no linear structure. It means the compatibility with this structure. Okay, I could write as a Lie group. Okay, as a Lie group into SON. And note, I just ask for a homomorphism. That means it's structure preserving map. Well, let's give it a name. Let's call that map rho. I don't ask for it to be a Lie group isomorphism, so it's not one-to-one. Okay. Indeed, it's the very definition of the spin group that the kernel of this map, the kernel of rho. Well, you know the kernel from linear algebra, where it's all those elements in the domain which are mapped to 0. Well, 0 is the neutral element of the group operation on a vector space, and that's the addition. Well, here the group operation is a different one. In any case, we want all those in the domain that are mapped to the identity in the target, to the neutral element, to the neutral element in the target, but in the group, of course, in a group, the neutral element is the identity. Okay, so where the kernel, that's just the definition of the kernel, where the kernel, and that's now the definition of spin, where the kernel is isomorphic to the group Z2. And you know Z2 is the group with just two elements. It certainly needs the identity element, whatever it is, and it needs a second element, and whatever the group operation is, E with E must give you the identity again. Okay, that's Z2. Okay, so again, a spin group is a double cover, and this double cover in the Lie group sense here simply means, well, in this context of SON, it means that you have a Lie group homomorphism which has a kernel with two elements. In other words, this map is 2 to 1. It's 2 to 1. So there are two here that map to the same over here. And not only two, there are always pairs that map to the same. It's a map that's 2 to 1. In other words, the map is 2 to 1. Okay? So that's the spin group. And we will construct the spin group explicitly, and we'll need to construct it explicitly in cases that interest us. Well, I give you the result first for various dimensions, and we'll concentrate on 3 and 4 dimensions, on 3-dimensional space and 4-dimensional space-time, which is still what seems to be the case out there. So let's look at the dimension n, okay? And let's write down what is spin n. And we'll also look at spin, well, I'll do that in a second. So in 1, 2, 3 dimensions, what's this spin n group? Well, what you all need to know is that in 3 dimensions, the spin 3 group, spin 3 is SU2. Okay? One can check this. So that if n is 3, then SU2 does this trick, and we'll study that in detail. Okay. In 2 dimensions, it's U1, I think. And in 1 dimension, it's O1. Okay? And that goes on. Now, if I say that goes on, one calls these here coincidental isomorphisms. So we have spin n is as a group isomorphic to okay, but in some dimensions there is simply no other simple classical Lie group where this fits in. Okay, at least not in this simple way, and so this seems like a complicated definition, but as soon as we understood this, we can of course work with this as usual. Okay, so so if people say, oh, SU2 is the spin, so if you see the spin 3 group, you know it's SU2. If somebody talks about U1, you would know it's spin 2. Maybe they use it in another context, but that's the case. Okay. Now I said here that we're looking at SON. However, we could also look at, so extension of this idea, look at a row that goes from SOPQ, that defines spin PQ, which is a double cover of SOP, Q. And by P, Q, I mean that I no longer have a positive definite inner product, but I have an inner product with P pluses and Q minuses in the Sylvester form. Okay, and obviously this is of interest in relativity because there we have the Lorentz group, SO13, and there we need that. Okay, so we can also ask about the spin P, Q groups. Okay, and I just give a few examples of interest, and the examples of interest to us are, well, if any, it's certainly the 1-3 example, because that's a Minkowski inner product, okay? So we talk about the Lorentz group that goes with it. The question is, what is the double cover? So this remains. So the idea is, again, that the kernel of rho still ought to be isomorphic to Z2, okay? So the question is, what do we find for spin 1, 3? What are the spinners in 3 dimensions? And it turns out it's SL2, well, it's isomorphic to it. So we can just take SL2C. You can't see this. We look at this, okay? So this needs to be proven. That's why I said result. So don't be puzzled. Then it's maybe interesting to look at 1 and 1,2. That's like you take a thin film or something and you look at electrons in there. Well, if the electrons are effectively constrained to this in this thin film, you of course have the Lorentz group SO1, 2, and there the spin group is given by SL2, R. It just so happens. SL is special linear, so it's the general linear group, but only those elements that have determinant 1. Right? Of course, this was incomplete. What I wrote down here is the orthogonal group. I have to restrict this to determinant +1. So this S here is this extra condition that the determinant be 1. I'm sorry, I suppressed that. And I think the spinners in 1, 1, so in 1 + 1 dimensional space-time, I think it's GL1R. But this one I'm not so, I think it's true. I think it's true. Okay. So here maybe we've been smarter. I mean, this is 1 dimension that goes like this. This is the 2 dimensions. Okay. This is 3 dimensions. I think in 4 dimensions that are Euclidean, so where you have plus signature, the spin group is SU2 cross SU2. So you see this is the 4 dimensions. And obviously there is no 0-dimensional space-time. Well, 1, 0 is just the time axis, whatnot. Okay, so these are these accidental isomorphisms, which I have a very, very useful to work with that. And we will now focus on this one. Okay, focus on this one. So we would like to construct, because that's obviously the case in non-relativistic physics, in physical space in the lab. It's 3-dimensional, and we want to understand spinor fields in there. And once we understand this, it turns out that this case here, which is the spin 1,3 group, that's of course the spin group in 4-dimensional space-time. Well, I should always say at a point, so don't be confused. If I say Rn to Rn, you shouldn't think of this as space-time. You should think of it rather as the tangent space to space-time, okay? Because it's only happening at one point, okay? And the whole point of the principal bundle approach will be to actually distribute this over the whole manifold, right? So very often we talk about Minkowski space as a vector space and so on. Well, that is very fishy, right? It's the tangent spaces to space-time that are vector spaces. So if I write here Rn, and we first have to get this algebraic stuff working, later on this will be identified with the tangent space to space-time. Okay, we'll come to that. Okay, so focus, so aim. Well, you could say, okay, why do you make this definition? Well, it will turn out to be important, okay? So we first have to work a little bit in order to have the structure we need. So our aim is to now construct a Lie group homomorphism rho that takes you from SU2 to to SO3, okay, that's the case we're looking at, such that, so it's a Lie group homeomorphism, such that the kernel of rho is the Z2 group. And in order to do this, we need to make a few observations, okay. Strategy, make a number of observations. Okay, so let me try to discover this with you rather than just provide the constructions. Well, so we want to talk about this SU2 group, and we found before, if we want to think about representations of the group, and that is certainly something, if we want to put our hands on this, it's good to write down a representation in order to work with numbers, okay? And how can you always represent a Lie group? Well, you can represent it trivially, that's not so interesting, but how can you always represent it? By the adjoint action, right? And what is the adjoint action? The adjoint action of a group is how it acts on its own Lie algebra, okay? And so that's always a way to get a non-trivial action. So whenever you know nothing and you want to get started, why not look at the adjoint action, okay? So the first question is, what is actually the Lie algebra, little su2, of SU2? Algebra of SU2. Well, you know that is a very long calculation if you want to do this properly in a differential geometric spirit, and I provided that to you in one of the previous lectures. Now we'll do a quick and dirty derivation, which is just 2 or 3 lines long, and the challenge is to match this to the formal derivation, and you'll see that the formal derivation is much more insightful, much clearer, without any ambiguity or question what means, but it's just most of the time not really necessary, okay? So we say SU2, let's get a definition of SU2. Well, we start with some matrix definition. SU2 contains all those U's that are complex 2 by 2 matrices, such that U dagger is the identity on C2, and such that the determinant of U is 1, right? Now the quick and dirty calculation how to get the Lie algebra is to consider a group element close to the identity, because of course if you have the identity and then you have another 2 by 2 matrix H for some H being a complex 2 by 2 matrix, and you use a small epsilon, of course in the small epsilon you recognize immediately there will be something with the differential. And very roughly speaking, if you make the epsilon small, this is like the tangent vector at the identity that takes you to an element close to the identity. You know how dirty this is because there is no such thing as an addition on the group itself and la la la. So this is all very dirty, and it's absolutely not possible to make any real sense out of this apart from the fact that it's exactly what you need to do. Okay, so if you say, okay, where does this plus live? And I say, well, it's the plus on the matrices. Yeah, but what on earth does it have to do with the group? Because this is a matrix group. The only operation is the matrix multiplication. Who on earth allowed you to use the addition of these matrices? Of course, you have this addition, but it could totally destroy the properties of the group and so on. So you can do this, and it's good physics tradition to do it, and it will produce exactly the right result. But if you really start to question this, what this actually means and why you can do this, you're pressed to go back to the formal definition of what the Lie algebra is. And I think we derived the Lie algebra of what group did we derive it? It was SL2C, right? So this, yeah, okay. So this is the non-relativistic version of it, and you see SL2C is exactly the one for SO13. This is the one for SO3, and so on. So here it's now the place to put in the quick and dirty stuff. But again, if you want to ask what this means, need to go back to the formal stuff. Okay, so but the idea, once you have this, it's incredibly simple, because we now evaluate this condition. That's 1 plus epsilon h times 1 plus epsilon h. Aha, and you now say, well, what kind of trick is this? I put an I here, and I can, because this is still close to the identity, and this is the addition on the complex matrices, so what the heck? It's just convenient to have the I there, okay? So we have this, plus I this, plus I this. Dagger is supposed to be the identity, so you do this left-hand side. This here is, of course, 1 minus I epsilon h dagger, okay? And now, of course, you use the binomial theorem, and you get 1 minus I squared epsilon, no, nothing I squared. Yes, I squared. 1 minus, hang on, what are we talking about? This is 1, yeah, exactly. What on earth am I doing here? Okay, so this is the 1 with the 1. So now comes plus I epsilon h, plus I epsilon h minus I. That's it. It's not the binomial theorem, because there's an h dagger and there's an h. That's why it's not the binomial theorem. Okay, 1 minus I epsilon h dagger, and then comes a plus order of epsilon squared term equals 1. Now, if we make epsilon small, or in other words, if we take the derivative with respect to epsilon at 0 and so on, what we see is that we can neglect this term, and we get 1 plus I epsilon times h minus h dagger is the identity. Well, in order for this to be true, for non-zero epsilon, it implies that this matrix, this kind of tangent vector, in a sense, needs to be a Hermitian matrix, h equals h dagger, right? If I hadn't put the I here, it would be an anti-Hermitian matrix. That's as good, yeah?
Epsilon is in R.
Epsilon is in R, that's right. Otherwise, it couldn't be smaller. Well, it could have small absolute value, but it couldn't be small all by itself. Okay, good.
And it suffices to just consider a complex factor in front of the h.
Well, that's the idea, because I want to go away in directions. So this is the curve parameter. I start at the identity, and I make a curve, okay? Then I take the tangent, and then I want to find out what the tangent vectors to the curve are. Right? I mean, this is as I said, it's dirty as hell, okay? Once you know the differential geometric definition, you say, what on earth are you doing? But of course, one feels it's still there, and the result won't be different if you do the full derivation. Well, that's not worth it, because I showed it to you once, and we all agree we don't want to do this again. Okay, so this is this, and the second condition is that the determinant of u, which is now 1 plus I epsilon h, that the determinant B1, that's the S in SU2. But then there's the determinant formula for the expansion of a determinant. So determinant of 1 plus something is 1 plus the trace of this something, I epsilon h, plus, well, higher orders in the something. So that would amount to higher orders in the epsilon, which we again forget about, but the trace is linear, so the I epsilon go out. The only way for this to equal 1 is that the trace of h vanish. Okay? So what we found is that the tangent vectors at the identity are traceless Hermitian matrices in 2 dimensions. Okay? And this space deserves a name, so define H to be the space of all the, how to call them, X's, capital X's. These are matrices. I could also say they're linear maps from C to C, but okay. They're matrices such that they're Hermitian and they're trace-free. Okay? Yeah.
What is the step from the determinant to the 1 plus trace?
That's just an expansion formula for the determinant. You can Taylor expand the determinant, and then the first term is a 1, because the determinant of the the determinant of the identity is 1, plus then comes a term linear in this epsilon, and it turns out to be the trace of H, and then come higher terms. So it's the Taylor expansion of the determinant, if you wish. Yeah. Okay, so that's this result. Okay, so I'm just claiming this, and you trust me. So this is this space here. So now, okay, so what are we talking about here? So we wanted to talk about SU2. Why did we look at the Lie algebra? Well, because we know that on this space, which is the Lie algebra, we can represent SU2. Okay? And how do we do that? Well, we can have an SU2 action, SU2 cross H going into H by taking a U and taking an element X from H and mapping this to, well, we know how that works, to the adjoint action of U on X, which is just Ux, and it is U inverse, right? But we see from U dagger is 1 that U dagger is the inverse of U. So in particular in this context, this is Ux U dagger. Okay, so what have we achieved? Well, we found some representation of SU2 on this Lie algebra. You say, okay, you can do this with any group. What's the special deal? Well, the special deal is that what we are after is a map from SU2 to SO3. Well, not any map, but Lie group homomorphism. Now, SO3 acts naturally on what space? So SU2 acts in its defining representation on C2, right? Maps from C2 to C2. SO3 in its defining representation acts on R2 cross on R2 from R2 to R2, and we know that this is R transpose equals the identity, but now in 3 dimensions, in 3 real dimensions, in R3, and the determinant of R is +1, right? We know that this is the defining representation of SO3. Now, if I had taken the defining representation of SO3 going from R2 to R2, and the defining one of SO2 going from R3 to R3, okay, and compared it to the defining representation of SU2 that goes from C2 to C2, they have nothing to do with each other. One is R3, the other one is C2. You can think of C2 maybe as an R4 with an extra structure, but it seems to have nothing to do with R3. But the trick is you can take this one, the representation space R3 of SO3, so it's the defining representation space, and compare it to this Lie algebra, because how many dimensions does this Lie algebra have? Well, the dimension, observe, the dimension of this Lie algebra, of this H, right, as a real vector space is 3. Because, roughly speaking, you have 2 by 2 complex matrices, but you require that X equals X dagger, but you know that X dagger is X transpose star, okay, in this very simple setting here. That means these 2 guys need to be real numbers, independent real numbers, and this can be a complex number, but this is simply that complex number from up there start, so there's no new information. So you have 1, 2, 3, 4 real numbers, but then there's also the trace-free condition, so this number down here must be minus the number up here, so you have R3. Okay, so dim of this representation space, and this is a representation space of SU2, this representation space has the same real dimension as the representation space of this representation. Okay? That is why this is now interesting. It's an accident. Okay? It's an accident, and that's the table I wrote down before with these accidents. Okay? So anyway, we're going to come there. Okay, so we found this guy. So we now would like, in order, before we can write down such a Lie group homomorphism, we might get an idea of how that works by having a conjecture and then proving the conjecture. And the conjecture is that, well, that's not so much of a conjecture. It's obvious that it exists, but it's interesting to see how it looks like. There must be, this is a real vector space of dimension 3, and R3 is also a real dimension, a vector space of dimension 3. We know that all the finite dimensional real vector spaces are isomorphic to R to the dim V, dim H in this case. So this is clear, okay? No?
Could you give me a quick argument why R3 cross 3 is also
No. Look, yes. So I confused you here. So this is right, what's written here. This is already the representing matrix. That means R is a linear map from R3 to R3. And hence, if I write down with these properties, this is the representation space of this group, because these R's are maps from V to V. You remember that a representation of a group was a map, we called it capital R. Now too many R's in here. A representation, let's call it curly R. A representation of a Lie group was the Lie group, in this case SO3, of the Lie group, into the general linear group over V of some dimension. And so general linear means it's all the linear maps that are invertible. You need this because otherwise you need to send the identity to the identity, and there must be respected, because you want this to be a Lie group homomorphism. If this is a group with some operation, blob, okay, then this GL is also a group, because you can always use the composition of linear maps. You make this into a group, okay, and this goes here. Usually it will be maybe some subspace, some subgroup of this here, but that's a representation. So you can consider SO3 as R's in end R3, in GL R3. But GL R3 are just the 3 by 3 real matrices that have determinant non-equal to 0. And if you then have SO3, you even know the determinant is +1. Okay? So that's the confusion. So it's not this R that's three-dimensional, but it's the representation space on which it acts. It's an accident that this guy is three-dimensional, okay? But I'm talking about the representation space in which it acts. Okay, so, well, this is not much of a conjecture. This is actually clear that this is the case. What's more interesting is, so this is as vector spaces. If I take R3 with the standard inner product, I can also show that as an inner product space, it's the same as H with a particular inner product we're going to define on H. So from now on, we should distinguish between the inner product on R3 and the inner product there. So this here is clear, but you know, in order to have an isomorphism, I need to construct a particular map. We know there is one, but then the claim is with respect to such a map, I can also show that with the standard inner product and here with an inner product to be defined, they're isomorphic as inner product spaces. Okay, so again, we want to construct this Lie group homomorphism, but the first thing we do, we construct an isomorphism of representation spaces for the various Lie groups, and that will become useful in defining this isomorphism this Lie group homomorphism we're actually after. I mean, I could write this down in line 1, and then you say, how on earth do you come to this kind of expression for this map? Well, that's what we're discovering. So I try to show you how the thinking could have gone in some, if we didn't know the answer already. So in order to write down explicit maps, it's useful to choose bases. So choose bases. And the first basis we choose is E1 equals 1, 0, 0. E2 equals 0, 1, 0. E3 equals 0, 0, 1 of R3. So note, so sometimes people are confused because they say, hang on, you provide a vector in terms of its components, but isn't the whole point of a basis to introduce a basis per se without already using components with respect to another basis? You know what I mean? But it's not like that. R3 is R cross R cross R. Agreed? So this is the space of 3 tuples. So this is an honest element of here without having chosen a basis. Okay? So good. Okay. So choose basis of R3, and we choose another basis, namely sigma 1 being this guy, sigma 2 being this guy, and sigma 3 being that guy. You see, I learned them meanwhile, as a basis of this H space, because obviously these are 3 matrices, they all are trace-free, they're linearly independent, and they're Hermitian. So they must provide a basis of H. And now we want to explicitly construct an isomorphism, let's call it mu, from R3 into H. And I do this by taking a triple here, x1, x2, x3, and map it to x1, yeah, that's correct, x1 sigma 1 plus x2 sigma 2 plus x3 sigma 3. Or if you want to write this in short form, you may want to write it like this, but this is the definition. Obviously, there's an element of R3, and quite obviously, there's an element of H. It's a linear combination. Now, an interesting question is, okay, and obviously it's linear, because there's the x only appearing once here, and it distributes linearly here. Now, we find explicitly, and it's useful to write this down explicitly, the inverse. So mu inverse from H to R3 is given how? Well, now you give a matrix capital X, which is an element of the, is a complex 2 by 2 matrix, but with the restriction that it be Hermitian and trace-free. Okay? And where do you send that guy? You send that guy to 1/2 times the trace of x sigma up I. And sigma up I here is exactly the same as sigma I, because we define the sigma up I's. Sigma up I, we define them as delta ij, well, with the indices up. It's actually not a delta, it's more like, well, it's a metric. Gij sigma j, right? Symmetric. But we use this here in this form. Okay, standard inner product. Anyway, that means as a matrix, it's exactly the same. It doesn't make a difference. Okay, so the sigma i's are sigma up i's are the sigma down i's, and once we do relativity, these will be defined with a relative minus sign. Hence, I explain it here explicitly. The index is up. It ought to be up because we want our indices on the components up in R3. So obviously, I have this, but now I want an element of R3. Well, very strictly speaking, I need to provide the basis vector here again, and I have a summation convention here and then I get an element of R3, right? Or you could say the first component is given by half trace x sigma 1, the second by half trace x sigma 2, and so on. Okay. So, well, I claim this. Again, this is linear. It's obvious that it's linear because the x appears here linearly. And this is obviously the trace over the 2 by 2 complex matrices, right? Because there's no other matrix inside here. Now let's quickly check whether this can be true, whether this is what we want. So we should check that something like mu inverse of mu of a little x, that this recovers the little x, right? And the other way around. Well, let's quickly write this down. So we don't want to assume this yet. We calculate it. Mu inverse is 1/2 the trace of mu of x times sigma I EI. Okay? And so this is 1/2 the trace. What's mu of x? Mu of x is x dotted into the sigma. So this is the xj sigma j summation convention, right? This is exactly this, xj sigma j. Agree? This times sigma I EI. Aha. So what's sigma j sigma I? Well, that's simple. We know, or we calculate quickly, that sigma I with sigma j down commutator is twice gij, where gij is again this thing, indices down is the inverse, but it's again 1, 1, 1, 1. So usually you write delta ij, but I don't like that because delta is the Kronecker delta, one index up, one index down. This is a bilinear form that transforms differently. The Kronecker delta is the same in all coordinate systems, in this context, in all bases, whereas the gij is not the same in all bases, right? Anyway, but we choose the basis where it has the simple form. You have this anti-commutator, looks like this, right? The commutator is up to factors, is the rotation algebra, right? The angular momentum algebra, but the anti-commutator is precisely this. So that means that here, because of the cyclicity of the trace, we have, of course, x up j. Well, I can write down here delta I down k if I write gki up here. You agree? But then this is the trace over the 2 by 2 complex matrices. These are just, for every ki is just a real factor, so I can pull it out. And then I have sigma j, sigma k here, and then I can write this as sigma j, sigma k, and because of the cyclicity of the trace, plus sigma k, sigma j, but I doubled the trace in this case, so I have to have another compensating factor of 1/2. This thing, bracket closes, EI GKI. Happy so far? So, but this is because of the cyclicity of the trace, nothing else. Cyclicity, well, of the trace. Okay. And now we use the anticommutator bracket is 1/4 trace xj 2 times g kj bracket closes ei g ki. So this guy again jumps out, but then k goes with k and gives you a delta ij. So this is, the 2 goes here, is 1/2 trace xj. And here you have still a 2 by 2 complex unit matrix. So everything goes, and here you have still the identity 2 by 2 complex, right? And they have your delta ij ei. So the xj goes out, but the trace over a 2 by 2 complex identity is 2, cancels this 1/2. So this is, the trace is taken care of. This is xi ei. And indeed, that's x. Very good. So mu inverse of mu of x equals x. Okay? And now, of course, you also have to check the other direction, but I think that we leave. Similarly, this is the case. So indeed, that's the proof. It's a linear map, this mu, and we explicitly constructed its inverse. Hence, this is an isomorphism. And we knew it has to exist, okay, because we know this is a 3-dimensional real vector space. It must be isomorphic to some R3. And now we constructed one such isomorphism explicitly, and that will be very useful. Okay? So it's not a surprise that it's so, but the construction will be good for us. Questions so far? Good. So now I made an extended statement. The extended statement is, so extended claim, that if I now equip R3 with its standard inner product, which now all the time I called small g, but it's just at one point an inner product on this, it's not a metric field over a manifold R3, it's just an inner product on this vector space, okay? I claimed that this as vector spaces has the same structure as H with an appropriately defined inner product on there. What does that mean as inner product spaces? It's isomorphic. Well, it means it's isomorphic as vector spaces and, well, in order not to get too confused, I called it before inner product on R3. Let's keep it there. I mean that there is an isomorphism between the spaces which we just constructed, and we need an additional condition in order to have them isomorphic as inner product spaces. And of course, what would it be? I take two elements of R3 and I take the inner product on R3, and then the result no, hang on. No. So I take the inner product, and that ought to be the same as the inner product on the H space, and this inner product we're going to have to construct, of the images under the isomorphism. Okay? This is what we mean by compatibility or isomorphism with respect to the inner product structure. So now let me define for you this inner product on H. So what does it do? It takes two elements of H and it produces A. So now let's be careful. This is, well, it needs to be a real inner product, because otherwise, hang on a second. Is this real valued? Well, it better be. Well, it's only under this map, but this map is yeah, I think it's real valued. So real inner product. Yeah, otherwise, okay. And what do? We take two elements, capital X and capital Y, so 2 by 2 complex matrices that are Hermitian and trace-free, and we define this to be, again, 1/2 the trace of X matrix multiplication Y. So this is the multiplication on 2 by 2 complex matrices. Okay, so I claim that's an inner product. Right. So why is it symmetric? Well, it's symmetric because of the cyclicity of the trace. Why is it positive definite? Well, you take the x squared, but that's an element always of these guys. You check that this is always non-negative or positive unless x is already the 0 map. And yeah, and in principle, you also have to check the triangular inequality. However, if you can show that this holds, then of course you know, because there's an isomorphism, this mu, you know this has all the properties that this guy has. Okay, good. So that's this guy. Yes, that's the right thing. So shall we quickly check? So I take, where do we best start? Maybe we start there. So proof. So proof of what? Proof of carpet, and this is the equation carpet. Okay. So let's start with the mu of some x and the mu of some y, where x and y are of course just elements in R3, vectors here, with respect to h. So what is this? This is 1/2 the trace times mu of little x, mu of little y. This is 1/2 the trace of, what was mu? Mu was xi sigma I. Then this here was the blob here, the blob here. This is yj sigma j, of course. And the trace, also here the trace is of course the trace over complex 2x2 matrices. So this is for every ij, this xi, xj are numbers. So this is xi, yj, and then we have the trace of sigma I, sigma j. Well, that guy we met before, we can write this as 1/2 the trace of this plus sigma j, sigma I, simply because the trace is cyclic, and then we can use that this is 2 times gij times the identity on the 2x2 complex matrices. This 2, because the trace is linear, goes against this 2, the trace and the gij jumps out, and then there's another trace over this complex matrix here, and that goes against this one. So what we end up with is xi, yj, gij, and that's precisely what we defined to be the standard inner product on R3. Okay? So yes, indeed, this inner product is the same as this one under this isomorphism mu. So again, we had the R3 with the standard inner product, and we saw that as inner product spaces, they're isomorphic. This one is isomorphic to H with the just defined inner product. And we know that the defining representation of SO3, so the vector representation, or the defining representation as we called it, acts on R3, and we know that the adjoint representation of SU2 acts on H. Well, it must, because H is the Lie algebra of SU2, and the adjoint representation is precisely this. It's the action of the group on its own algebra. Aha! But now we can check whether the adjoint action really keeps this inner product invariant, which if it does, we can use all these constructions, and that works because the vector rep keeps exactly this inner product invariant. Now the question is, does the adjoint representation keep this inner product invariant? And, well, you bet, because keeps this inner product invariant. Because, well, let's look at it. We take add u acting on some x, add u acting on some y. Well, this is, of course, 1/2 trace add u on x dot add u on y, because that's the definition of this H product. And this is 1/2 trace u x u inverse, well, or u dagger, it doesn't matter in this context because it's SU2, times u y u dagger. But now this is the identity, and you can also pull this u dagger here because of the cyclicity of the trace. This is yet another identity. This is 1/2 trace x dot y, and this is just x, y, h. Aha. So the adjoint, so the defining representation on R3, SO3, was defined as the transformations that keep this inner product invariant and have determinant +1. The adjoint representation here was not defined by keeping any inner product invariant. It was, well, originally the SU2 has of course a defining representation by keeping some Hermitian inner product invariant, but that's certainly not this one. But now the adjoint one can be understood as the group that keeps this inner product invariant. Okay, so now we have all the elements together, and we can now dare to conjecture that we have a map from SU2 down to SO3. Let's call this map rho. That's a Lie group homomorphism. And I need to write it down. And so I need to take a matrix in SU2. Hang on. Right. So I need to take a matrix U in SU2, and I map it to a matrix rho of U in SO3. And now I need to tell you how this map rho of U looks like. So if it lies in SO3 and should lie in the defining representation of SO3, it needs to be a linear map from R3 to R3. Now this map I define. So I define this image as a map because the image is a map. Okay? So this is rho of U acting on a little x that comes from R3. And I define the map if I define it for all x in R3. And I need to define element of R3. No, I can do this better. I can do it without the x. I define the U to be, now I'm no doubt inspired by the constructions from before. Trying this a little, you use 1/2 trace. You take the U, I'm a bit confused. You take the U, sigma, something is wrong. Hang on a second. Sigma I, sigma J, epsilon I, tensor EJ. Yeah, it's not linear. That's the trick. It's U, sigma I, U dagger, sigma up J. Yeah, can't be linear. Yeah, that's my definition. That's how I define this map. So I associate with a SU2 matrix U. Well, with an SU2 matrix U, I associate an SO3 matrix. I claim it's an SO3 matrix. We have to show this. Rho of U defined by 1/2 the trace. This is the trace over the complex 2x2 matrices. I employ this U matrix. Then I take the sigma I take the U dagger. I take the sigma up J. Then I have IJ running from 1 to 3. And I use here, and the epsilon I is the dual basis to the east that I defined. So epsilon I acting on EJ is delta IJ. It's the dual basis of the dual space. This is a complex matrix, okay? But the trace of it is real. One can check that. So I have real numbers, IJ. So this whole thing is an element of GL3R for sure, because this eats a vector and this spits out a vector. this is of course a basis for linear maps from R3 to R3. Okay, and these are its linear coefficients. So it's clearly an element of here. In fact, SO3 is an element of here. So that's an element of GL3R that I see immediately. That's an element of SO3, so of a particular subgroup of this I need to show. Okay, so but I construct this map. So I have to obviously need to show a number of things. So proof, we need to show. So the first thing we need to show is that indeed rho of SU2 just only takes me to the SO3 subgroup of GL3R. Okay? So that we, no? Okay, so let's try to do this first. So how do we do this? Well, we have to check whether if we take the rho u on an x and the rho u on a y, so remember this is a unit, this is an SU2 matrix, but rho of u is an SO3 matrix. Well, if I want to show that this rho of u is SO3, I must calculate and I must get the inner product of x and y, because that's the defining property that it be in O3. And then I also need to calculate the determinant of rho of u, and that's 1, and then I'm done. Okay, so let's first calculate this guy. So this is now the inner product on R3, but now we're trying to be clever about this. So this is the inner product on R3, and we already know that if I take this inner product and I apply a mu to it, then I can convert it into an inner product on H, right? So I know that this is the same as an inner product on H once I apply the mu to it. Agree? Because we had this thing inner product of mu something else is the inner product on H. Sorry, without the mu, then apply the mu. Okay, we just proved this. This is this. But now you see, remember what the mu was. The mu was in particular the inverse of the mu inverse. Okay, let's not be silly. So what was mu inverse? Mu inverse went from H back to R3, agree? And it was x being sent to 1/2 trace of x sigma I EI. Is that correct? Is that what we defined? I think that's what we defined, right? That was the back transformation. And don't we see so nicely here that our definition of rho of u is precisely something of the type, it's a mu inverse, it's the mu inverse of this being, taking the role of this x here, it's the mu, hang on, so this is mu inverse of x, so it's the mu inverse of u sigma I u dagger epsilon I, hang on, and mu inverse sigma j. Yes, and this is a vector, that's the point. So the mu inverse goes back to R3, exactly. So there should be, well, it depends on how you want to write this tensor product. You could also have written EJ tensor epsilon I, and then this is simply epsilon I. This may be better because it first accepts a vector from the right and then it spits out a vector. It's better up there. And so now the point is that this entire guy here, is of course precisely this here, because this is the sigma j EJ, and this is the sigma, well, can make a j out of this as well, EJ. Okay? Yes. Yes. So this is a vector, depending on what I is, one vector, the other vector, the next vector. No, I is just a number of this basis element here. That's this guy. Aha, but if rho of u is this guy, and we have here mu of rho of u on x, then we have mu of mu inverse of. But that's simply u sigma I u dagger tensor epsilon I acting on the vector x, right? Because it's a map that acts, comma, u sigma j u epsilon j acting on the vector y on this H space.
But the mu also, shouldn't it also act on the epsilon, on the tensor epsilon, if we leave out the mu and the mu inverse, but nevertheless the mu has to act on the epsilon, doesn't it?
The mu?
Because it's not inside of the mu inverse.
No, this is all inside. Mu of the entire thing. Ah, yes, but okay. Hang on. Rho of u of the inverse of the mu. Okay, what does the mu act on? But the mu only acts on the this H. Yeah, but it doesn't act. No, it doesn't act on it. I mean, it's. I see what you mean. So you say it's the result it acts on. So this is what you want. You No, but it's fine. It's fine. No, I mean it's so it's the mu of the. So it's clear that what is left here is. I see. I see your point. I just don't think it acts on there. Okay, let's write it. I see your point. You say the. It's true that this is the mu inverse of this and then tensored with this. And so this makes sense because this is an element of H. Now this is this map here. Aha, yeah, but it's simple. Okay, I simply, okay, you're right. So, okay, let's do it properly, but it's it all seems to be fine. So this is again the H inner product. And so now for your peace of mind, I write it out. It's mu of, or after, well, of mu inverse, so let's calculate this, of u sigma I u dagger, that correctly ends here, tensor epsilon I on x, close bracket. So far, so good, right? And then the same thing again, it's mu of mu inverse of u sigma j u dagger, thing closes, tensor product, epsilon j acting on the y, bracket of the mu closes, and the bracket capital H closes. Now, I simply evaluate this. Once I evaluate this, this is just a number xi. Okay? And now the mu and the mu inverse, here you still see it, they're both linear. So I can pull the I in or out. So I decide to pull the number xi and the numbers or numbers xj in. So I use the summation and so I use the full linearity, scaling and additivity. I pull this in and Right, I pull this in, that's correct, that's correct. And then I really have mu of mu inverse, and that's it. Okay, and then mu of mu inverse goes away, so this is u sigma I u dagger xi, comma u sigma j u dagger yj, all with the h inner product. Yeah?
When the x and the y is plugged into the epsilon, the tensor product is, we can get rid of this.
Yeah, it's just a number.
Because
That's right.
Yeah. But now it says something tensor product number, and this is a little bit strange.
No, it's exactly the definition of what the tensor product does, because if you have maps T tensor S and you apply them to omega comma E or something, then, to omega cross E, then it's exactly T of omega times S of E, and that's this times, that is the definition of the application of the map, and the epsilon is a map on these guys.
Yeah, that's right, because precisely because of this, the tensor product should be
Yeah, exactly. That's the dot. That's right. Thank you. It's yeah, that's fine. Very good. Okay, fine. And now we use the definition of the H inner product, and you remember that was 1/2 the trace of the product of everything that's in there. But the xi and xj for every ij is a big sum, and the trace is linear, so xi yj. And there's just the trace of u dagger sigma I u dagger sigma j u dagger. And of course they all go, there's one dagger too much here, this one is wrong. So they were wrong, right? So this is the identity. This is the u dagger by cyclicity. Also the identity is the trace of the sigma I, sigma j. And sorry, it's 1/2 the trace. And we calculate the number of times. That's 2 times gij. The 2 goes against this 2, tralala. In the end, what we get is the inner product of x and y over R3. And that's exactly what we wanted to show. So from this, it follows, so from this calculation, it follows that the row of u is certainly in O3. It's an orthogonal transformation. It's not yet SO3. In order to show that it's SO3, you also have to calculate the determinant. To show row of u lies in SO3, show that the determinant of row of u, so this is now the determinant over real 3×3 matrices, that this is 1. And the trick here is you need to use the epsilon definition of the determinant of an endomorphism. Okay. Anyway, problem sheet. There may be no problem sheet, but you know, if I write problem sheet, that's it's an imperative. Okay, good. So we have this. So what we did so far, we showed that indeed the map, the funny map we defined here, really takes SU2 to SO3. Okay, but we wanted to show much more. We wanted to show that it's a Lie group homomorphism. Still to show that this map rho is a Lie group homomorphism, so rho of two guys from here, one after the other, is the same as the composition of two guys of the images here, right? Still to show that this is a Lie group homomorphism. I also leave this to you, because it now always works like the stuff we did before, problem sheet. And finally, we want to know what the kernel is. What's the kernel of rho? Well, let's look at this. The kernel of rho, those are all elements u in SU2. for which the map we just constructed, rho of u, and what was this map? It was 1/2 trace u sigma I u dagger sigma up j ei tensor product epsilon up I, and it was the e j, okay, that this guy is actually the identity map on R3, but this it is if the components of it are delta ij or delta ji. Agree? That's this guy. So now again, it's a matter of playing around a little bit with it, but it's pretty clear that if u in SU2 here is a solution to this, then also minus u is. No? Because the u appears there quadratically. Okay? And from this you learn that there are two in there. Okay? Good. Okay, so thus spin 3 equals SU2 as claimed. Okay, so all we did is prove what before in the table I claimed for one special case. Okay. Good, good, good. But we have the explicit map that does it. The explicit map is our map rho. And that's good. We need that. Okay. So again, reminder, the R3 is to be understood with the tangent space at some point of a three-dimensional manifold in everything we did so far. Okay? And now we want to put this over an entire manifold. So we make the following definition. A spin frame bundle, is a principle, a spin frame bundle over a three-dimensional manifold M is a principal SU2. Well, let's not be silly. Okay, a spin frame bundle over an n-dimensional manifold. Let's not do 3. An n-dimensional is a principal spin n bundle with the pretty name P, totally new, that the principal bundle is called P, okay? And all I do is I take a particular group, namely the spin n group. It's a principal spin n bundle such that, the whole diagram is such that from there I have a map to the orthogonal frame bundle OLM over M. So this is the pi of the orthogonal frame bundle. Well, you know what the frame bundle is, LM. And the orthogonal frame bundle requires that every frame, so OLM is like LM, is like the frame bundle, with the restriction, so I don't allow all frames, with the restriction that if I have a frame that the EI and the EJ, and now orthogonal I can only do if I equip the manifold M with the Riemannian metric. So this be a Riemannian metric. Did we define in this course what that is? Well, a Riemannian metric is a second rank tensor field, so it's an element of the sections of T0 to M that is symmetric. Gxy is Gyx, but now x and y are tangent vector fields to the manifold, and that is positive definite. That means g of xx is greater or equal to 0 for whatever vector fields, and the equal to 0 if and only if the vector field x is already 0. That's it. Okay, so that's a Riemannian metric. I equip the manifold with this metric. And if the M is equipped with this metric, I can, in particular, if I have a frame at a position M, I can require that pairwise all these frame vectors at the point where I am give me this. That only if I take the first with the first, I get 1, and that all the first with the second gives you 0, so they're orthogonal to each other. They're orthonormal. Okay? And so this is the orthonormal frame bundle. It's like this one, but I restrict to only frames that satisfy this condition. And in order to do so, I need a Riemannian metric. I can't do this on a smooth manifold. Okay. So, such that, this is a principal spin n bundle, such that, well, first of all, such that this diagram, where there's a map phi up here, that this diagram A commutes. So you can first go from the spin bundle to the orthogonal frame bundle and then project, but that's the same as if you had projected immediately. That's the first thing. And the second condition is that this is a bundle morphism, and it's that phi, this bundle morphism, is supposed to be row equivariant. What does that mean? Well, we met that before. You see, if I now want an equivariance condition, I have a group here. The group can act on the total space, and I act on the total space with a phi. So I can take the phi and apply it to a point P in here. But because this is a principal bundle, there is a spin n right action. So let's call it U. Okay, a spin n right action and an element of spin n, let's call this U. And I want to require that this is compatible, that I first map the point P over here, but now I'm on the orthogonal frame bundle. And I would again like to act from the right, because this is also a principal bundle. I act on the right. It's another right action on here, so I should make this the solid right action. So this principal bundle comes with the solid action. This principal bundle comes with the non-solid action. It's a different bundle. But I cannot act on here with spin n, because spin n only acts on here. Well, that by definition it acts on here. But I can, of course, act on here with SON, if this is an n-dimensional manifold. And that is, of course, will keep this definition invariant. Right? If I act with SON, I don't upset this, because SON at the point is exactly designed to keep this invariant. So really by acting with SON here, but how do I make the U that is spin n, how do I make it to an SON? Well, I need a double cover map rho that does the trick. So this is the case, and where rho from spin n to SON is a double cover map. well, that's exactly what we constructed before for the special case of SU2 to SO3. Okay, so this is a spin frame bundle, and the data you need to provide for this, the data are obviously, this is all wet, the data you need to provide is obviously this total space and this map into the orthogonal frame bundle. So once you're given an n-dimensional Riemannian manifold, you can actually, you need to provide this spin total space and this phi such that this is satisfied, and well, this is also a double cover map and so on. And then you construct it over the Riemannian manifold, or rather over the principal bundle associated, to which this Riemannian manifold is associated, or is the base space of. If you provide these data, you provided a so-called spin structure. So this pair of data, P phi, is called a spin structure for Mg. And a natural question is, does it exist? Does it exist? And the complicated answer is, it exists if and only if the second Stiefel-Whitney class vanishes. And that's a topological invariant that you can look up how to calculate. Now, for our special case, there is a nice theorem that says when it does that, a Riemannian manifold admits a spin structure if and only if the second Stiefel-Whitney class, which is a topological invariant, we're not treating here, but you can look that up, vanishes. So that means you can always decide whether you can put such a spin structure on a Riemannian manifold. Special case is the dimension of M is less or equal to 3. So we won't cover space-time. Well, anyway, as I defined it, it's anyway only for Riemannian manifolds. But of course, this can be extended naturally to spin 1, n minus 1, and so on. Dim M less than 3. And then if M is compact and M is orientable, then a spin structure exists, always exists. Well, compact, we know it's a topological notion. What's orientability? Well, orientability can actually be defined in terms of the chart transition maps. If you can restrict the chart transition maps such as to have positive Jacobi determinant everywhere, and you can restrict the atlas such that you still cover everything, then the manifold is called orientable. So this goes back right to the beginning where we impose structure. Okay, so e.g., quantum mechanics on a sphere, right? On a sphere, on an S2, you can establish a spin structure because it's compact, it's orientable, and has dimension less than 3. Or less or equal to 3. Okay, but also if you do quantum mechanics in physical space, well, the compactness is a problem. You need to somehow restrict your physical space. If you take all of R3, it's not compact. Well, it doesn't mean it's not if and only if. So I mean, this guarantees it exists. The spin structure exists on R3 with the Euclidean metric, flat metric. It should also exist. Okay, so that's this thing. So, okay, so we have existence theorem, and there may be obstructions. Okay, so not for every Riemannian manifold there exists a spin structure. Well, it's a special case. Then let's go the other direction. A generalization is same construction for spin 1, n minus 1 on Lorentzian manifolds. And a Lorentzian manifold is like a Riemannian one, but this positivity definition is weakened to saying G, if for all x, gxy is 0, then already y is 0. Well, that's pseudo-Riemannian. It allows you any signature. So if the signature of this guy, of this bilinear form, is 1, n minus 1, that's a Lorentzian manifold of dimension n, like we have it in general relativity. And then you do the same construction. All is fine. The question is, why on earth do I want a spin structure? Well, I want a spin structure in order to define spinors. Definition: a spinor field, right? A spinor field is a section of a spin bundle. Not of a spin frame bundle. This is a spin frame bundle, and now of a spin bundle. So I should tell you what a spin bundle is. Definition: a spin bundle is a vector bundle with typical fiber F, it's a vector space, associated to the spin frame bundle, by virtue of a linear left action. Now, if you have a frame bundle, you have a principal bundle. Sorry, if you have a principal bundle, you can write down an associated bundle if you provide a left action on the fibers you want to have. By a left action, well, a left action of the spin group that you have here, so whatever signature, on this fiber. It's a linear, supposed to be a linear action. So if you fix spin, then this is a linear. If you fix the element from spin, then it's a linear map. By virtue of a linear left action, that is a representation of spin. So you want this to be a representation space, right? That is a representation of spin. Okay. Aha. So that means these fibers are the values in which our spinor, that's the space in which our spinor field takes its values. Okay? And we want to understand, this needs to be understood as the associated bundle to the spin frame bundle. So we need the spin frame bundle in order to say what the associated spin bundle is, and the spinor field is just a section in the spin bundle. Okay? And because of this construction here, you know, if you do something in the spin frame, it has a bearing on the orthogonal frame. Right? And that's what we do in physics all the time. We say we rotate our measurement or our macroscopic classical, well, non-spin apparatus by 2 pi. Okay? And then, however, we have only gone from here, say, from the identity to, we only rotated the spin half the full angle. And then we have to rotate the apparatus once again, and then the spin has come up to where we were. Okay. Now the question is, why did we have to constrain to the orthogonal bundle here? Well, we showed that the orthogonal bundle is, of course, precisely the bundle that's kept invariant by action of the SON group. one could ask, what if we hadn't taken the orthogonal bundle? So if we don't ask for a metric, then we have here the frame bundle. That's a principal GL bundle. And the question is, are there double covering maps? In other words, are there spins corresponding to GL like there are spins corresponding to SO? The answer is no, they are not. Hence, our understanding of spin is something that requires an underlying metric. An understanding of tensors only requires a smooth manifold. That's how we constructed them. But if you go from tensor to spin, you already need a metric geometry underlying, or a Lorentzian geometry underlying. In that case, it's SL2C, and spin 1,3 is SL2C, and so on, in order to even define spin. Okay, so it's sometimes said in particle physics books or field theory books that, yeah, tensors are fine, but spins are more elementary. Well, that's true, because I can usually use spins to construct tensors and so on, right? Because this is the double cover, so if you understand this, you understand this, okay? But you only understand the OLM. You don't understand the full frame bundle. That's the point. Okay, so it's true that on a Riemannian manifold, a spin is more elementary than tensors, but tensors are there even if you don't have a metric. Okay, so our concept of spin that we have depends on having a metric geometry. If you didn't have a metric geometry, like some theories use, then it's not so clear what the spin is supposed to mean. Okay, and then this needs a review. Okay, good. So that's the construction. It's very abstract, but when you go to the literature, well, now you have a frame bundle, and you see you have sections of an associated line bundle. Now you want to construct the spin covariant derivative, as you find them in general relativity books, the spin covariant derivative. If you look at this just in a standard formulation, you write down all the formulae, but the understanding is clear. A section of the associated bundle can be made into a spin n equivariant fiber-valued function on the spin frame bundle, like we did it last time. Then you can push the whole thing down by choosing a particular section of the spin bundle. You get the local version in terms of Young-Mills fields and so on. And the formula in general relativity books you find for the spin covariant derivative, sometimes mysteriously defined there, is exactly the construction we did before for general covariant derivatives of sections of associated bundles. Okay? So if you only think about the spin, you forget this part. This is just to define how this P needs to be constructed, and you do the construction from last time, and you get the spin covariant derivative. It's just the covariant derivative that has to do with choosing a connection on the principal spin n bundle. It's totally exactly the same as we did before, now for the spin n bundle. So there's no mystery what the spin covariant derivative and the spin connection and all of that is. By spin connection, people usually mean the Young-Mills field of the connection chosen on the spin n bundle, the push down, the pulled back Young-Mills field along the action, section here. Okay, so all this unifies, it actually precisely defines what you find in GR books. So unfortunately time is up, so I'm not going to write this down in more detail, but if in the future you meet this, you can refer to here, and then you really understand what's going on in standard fashion.